Hello. Just before starting in the new section, just to recapitulate what we had last time. So last time we have introduced the Huffman codes. Huffman codes as an example of entropy codes. So how to reduce the average word length or average length of the encoded message by using variable length codes. So the idea is, based on the probability of individual symbols, I will assign to each of the symbols code that has either shorter length for oftenly occurring symbols like B, or longer codes for seldomly occurring codes. And it is based on constructing coding tree. And this coding tree, as we have shown, has such a structure. It has a non-uniform structure. The symbol that has the highest probability of observation is obviously closest to the root of the tree, while the symbols that are of very low probability, they have a rather long path to the leaf, meaning they have a longer code. And we have shown that in this example, we have average code length that is identical to the entropy of the source. So it's like a fabricated example. I have an example where I have chosen the probability of symbols such that in this example, the average length code that is simply number of bits for the first symbol times its probability, plus number of bits for the second symbol times its probability. When I add up this for all the symbols, I get 1.75. And if I compute the entropy according to the definition of the entropy, and that is this expression here, so negative sum of the probability times logarithm base 2 of probability, if I compute the entropy, I will get exactly the same value, 1.75 bits. And that shows that the entropy is the measure, a lower bound of the coding length for average coding length per symbol. So we cannot encode this source with any shorter average code length than is the entropy. So entropy is this theoretical lower bound. And that is true only when the source is memoryless. So when we don't have any conditional probability from this sample to the other sample. So from one symbol in the observation sequence to another symbol in the observation sequence. When they are completely statistically independent, then we can say, okay, indeed, I cannot encode this source any more efficient than given by the entropy. But this code has a problem. And the problem with these Huffman codes is when one of the symbols has very high probability. I have written on the whiteboard one such example. Let's say that we have only two symbols. And if we have two symbols, we don't have any opportunity in building the coding tree except having such symbol tree, symbol 1, symbol 2. For example, 0 and 1. We have 1-bit code for symbol 1, for example 0, and we have 1-bit code for symbol 2. We don't have any other opportunity than to construct such a binary tree. Although the probability of this symbol is very low, for example, first symbol or the second symbol is very low, so P2 is 1 over 32, and P1 is 31 over 32. So this first symbol 1 is occurring much more oftenly. And now if I compute the average bit, the average length of the code, the average length of the code is simply P1 times 1. This is 1. The length is 1. Plus P2 times, again, 1 bit, because this size is also 1 bit in length. This code is also 1-bit code. And we get P1 plus P2, and that is 1. So the average coding length for per symbol is 1 bit per symbol. So we cannot encode this better than 1 bit per symbol. Whatever I try. But what is the entropy? The entropy is much lower than 1 bit per symbol. The entropy, if I compute the entropy according to the definition as a negative sum of probability times logarithm base 2 of probability, and if I substitute the actual values of these probabilities, 31 over 32, times this logarithm base 2 of the first probability, and 1 over 32 times 5, because it is 2 to the power minus 5. And if I compute these values, I get the entropy of only 0.2 bits per symbol. 0.2 bits per symbol. And that means that the actual entropy is five times lower than the average coding length in the case of this Huffman code for this example. So obviously, we can then say, okay, for example, if this probability is going even lower than this, in this case, the first term will be very close to 0. So this first term will get smaller and smaller. And the second term is getting larger, but again divided by some small probability. What comes is this probability goes to 0. The entropy goes to 0. Because what happens is that if one symbol is constantly in the output, for example, symbol 1, 1, 1, 1, 1, 1, 1, and only in 1 billion times I have 2, then the average coding length, minimum coding length is practically 0. There's no information. You only hear 1, 1, 1, 1. There's no information conveyed to you. Only from time to time you hear 2, okay, and that is the information. So if I compute this entropy as a measure of information, I have almost 0 information for such sorts. But if I have to encode it with the Huffman tree, I have to encode it with 1 bit per symbol. I cannot go lower than that. So the suboptimality of such Huffman coding is at most 1 bit per symbol longer than the entropy. So if I compute the actual entropy of the source, and if I construct the Huffman tree, I will get the average coding length per symbol that is at most 1 bit worth longer than the entropy. So that is the suboptimality of such prefix-based encoding. And the second technique for entropy coding, for entropy compression, was introduced by this guy. That is, his name is Jorma Risanen from Finland. He worked for IBM at that time, and he decided somehow to solve this problem. So when you have a message, and when some of the symbols are occurring very seldomly with very small probability, and only a few symbols maybe are having probability much larger than that. In this case, so what he decided, why not encode the whole message at once, not symbol per symbol, but why not encode the whole message as one entity, as a one long number in particular. So his idea was, why not construct one number, and this number would represent the whole message. And the technique that he used to construct this number is rather simple, rather straightforward. It's quite astonishing that nobody else came to this idea before. Because the idea of this guy was to simply divide the interval from 0 to 1, representing the total probability of all symbols in the source. So this is the interval from 0 to 1. And I have, for example, in this case, 6 symbols and one additional symbol, $, that will be used to represent the end of the message. So I have, for example, alphabet that has only 6 letters, A, B, C, D, E, F, and last symbol, $, to represent the end of the message. And he said, okay, if I write that this probability of symbol A is 1 over 5, 1/5, 0.2. Probability of B is 0.1, 1/10. C again 0.2, D 0.05, symbol E 0.3, symbol F again 0.05, and finally probability of this last symbol, this auxiliary symbol dollar, is again 1/10. And what he said, okay, if I know this probability, I will simply assign interval range for each given symbol. So any real number in this interval from 0 to 0.2 will be good enough to represent symbol A. So I can select any number, 0.19 for example. And this 0.19 as a number completely describes, okay, it falls in the interval 0 to 0.2. It means that this symbol behind the number is A. Okay? And analogously for all other symbols, so the second interval starts from 0.2 up to 0.3 because the probability of symbol B is only 0.1. So it is twice narrower interval than the first one. Then symbol C, again 0.2, so from 0.3 to 0.5. Symbol D from 0.5 to 0.55, blah, blah, blah. Finally, symbol dollar from 0.9 to 1. And I have covered now the whole range from 0 to 1 because the sum of probabilities, of course, must be 1. So this is a histogram. Okay. So when we encode the first symbol, we concentrate only on the subinterval corresponding to that symbol. I will maybe show it in the actual example how we do the encoding or decoding. For example, let's say that we want to encode the message CAEE $. I want to create a number that will encode the whole message at once. So we start, we initialize in the step 0, let's say, lower bound is 0, upper bound is 1, and the width is 1. But now we know that we have to encode the first letter C. And for that reason, in order to select a number to represent letter C, I have to select a number in the range from 0.3 to 0.5. Why? Because it is the range corresponding to the symbol 3. So any number 0.3 to 0.5. Okay. Now, this interval, 0.3 to 0.5, that is 0.2 in width, is subdivided in the same way as the original interval 0 to 1. So the original interval 0 to 1 was subdivided into regions based on probability of symbol A, B, C, D, E, F, blah, blah. And now this range from 0.3 up to 0.5 is subdivided in the same relative width as the original interval. And if I know that the second letter in the sequence is letter A, then in this case, to encode C and A together, I have to select a number from 0.3 to 0.32, 34, sorry. Why? Because this 0.3 up to 0.34 is this range here. So 0.3 to 0.5, but now this 0.3 to 0.5 is subdivided into sub-regions in exactly the same way as the first interval. And now I can easily compute that this upper bound for the symbol A is 0.34. So any number between 0.3 and 0.34 is good enough to represent symbol C followed by symbol A, CA. Okay, and now that I know the new upper and lower bound of the interval, I write it here again, from 0.3 to 0.34. Now I again subdivide this interval in the same relative ratios, and the next symbol should be symbol E. And this symbol E is this one here, this region here. And if I compute what is the lower bound for this symbol E, what is the upper bound, I can easily find this is 0.322, and the upper bound is 0.334. So I iteratively compute this lower and upper bounds based on the symbols observed. So now it is E, then again it is E, and finally it is the last symbol $. So CAEE $. So the last range that I have come about at the end is this range 0.33184 to 0.3322. So any number in this range is valid to represent the whole message. So the whole message is decoded exactly as CAEE $, as long as I take any value, any real number, any real value in this range, from 0.33184 to 0.3322, any real value. And to show that it really works, we will do the decoding and we will select one particular value to represent the message. And this particular value will be, let me check, this one, 0.33203125. I'll write on the whiteboard just to have it as a reminder from which we start. 0.33203125. Why have I chosen exactly this value? Because this value has a nice and short binary representation. It is actually a fractional binary number that is 12 bits in length. So this is not just any number. It is written here. So this value B in binary form is actually 0.01010101, 01010101, and 4 zeros. So altogether I have 12 bits here. The weight of this bit first is 0.5. The weight of this one is 0.25, blah, blah, blah. Okay, and if I add this non-zero values, so it is 0.25 plus whatever, and when I sum this up, I will get exactly this value, B. Okay, and now we will start from this B. We have to check whether this B is really in the desired interval. Desired interval was 33184. Okay, it is larger than 33184 because it is 332 something. Is it smaller than 3322? Yeah, it's smaller than upper bound. It is 03320. So it is indeed in the range as required for the whole message. So it must be greater than 0.33184 and must be less than 0.3322. Okay, and that's valid. That's checked. Now, how do I decode this message? So I start from the value that I have written on the whiteboard. I first check in which interval this value belongs to. And if I check with the original coding table, let's say coding table is this original subdivisions of intervals. So this value, 0332, is somewhere in this interval. So obviously, I'll write, okay, the first letter is C. Why? Because B is larger than 0.3 and smaller than 0.5. So the first symbol is C. It is in this range. What I have to do now is subtract this lower bound, minus 0.3 from the value, and after that divide with the width of this interval, divide by 0.2. So the whole idea is simply subtract from B the lower bound of the interval that B falls into, And once I subtract this lower bound, I simply divide this value after subtraction with the width of the interval that I have decoded. And that is then written in this table. Okay? So I subtract the value of 0.3 and divide with 0.2. I get 5 times 0.03, blah, blah, blah. And when I compute this value, it is 0.16015,625. Now I have to check the interval corresponding to this value. And of course, it is the first interval, the interval for the letter A, because A is from 0 to 0.2. So I write, okay, the next symbol is obviously symbol A. Again, I subtract the lower bound, but since the lower bound is 0, it is the same value. And I have to divide with the interval width of the symbol A, and that is again the same 0.2 as for the symbol C. There is no difference. So I simply get 5 times this value, and 5 times this value is 0.800781225. Now I have to check this interval. Let me check where this symbol E is. Sorry, symbol E is from symbol E is from 0.55 to 0.85. Okay, so it is in this range, 0.55 to 0.85, this range. So I simply write, okay, the third letter of the message is E. Because this is the range for the symbol E, I have to subtract this value, 0.55, from this value, and then divide the difference with the width of the interval, 0.3. Okay? And I get the new value. The new value is 0.8359. Again, in the same interval, between 0.55 and 0.85. So obviously, the fourth letter is again symbol E. Again, I subtract 0.55, I divide with 0.3, and what I get is the final value is 0.95. And this interval corresponds to symbol $, the last symbol that indicates the end of the message. As soon as I get this value, $, as the output symbol, I know that I have to stop. It's enough. I have decoded the whole message, and I have found out the decoded value, let's say, okay? So it is rather simple. It is based simply on subtraction and division. Okay, and now the only question is how to find this value. So how can I come out with this exactly the value of B as chosen here as a 12-bit binary fraction number? So how to find this value? And the algorithm how to find this value is written here. Let me check here. So this algorithm how to find the value of this number B, okay, set B to 0 and counter to 1. As long as B is less than the lower limit of the interval, set the ith binary fraction to 1. But if now B is greater than the upper limit, return the ith digits to 0. Let me check with this example here. So in our case, I have to encode this range. I have to encode this range here. So I try to set the first bit to 1. So it says here, set the first bit to 1. Okay, is it greater than the upper limit? Yeah, it's greater than the upper limit because the upper limit is 0.3322. Okay, I give up, return it to 0. Then I move to the next digit. Now I set this value to 1, and this is 0.25. Okay, is it now larger than the upper limit? No, so I keep it. I keep it. Then I go to next and go on. So finally, the question is, how do I know when I have to stop this loop?
Yeah, but apart from the first bit, the whole other bits are lower than the clean upper limit. So we keep them all.
You end up together. So you simply take, this is 25, so you have to accumulate. We have to accumulate the values.
Okay.
So I have set this to 25 and I keep it.
Yeah.
Now, for example,
125.
when setting this one will be 0, 1, 2, 5.
Yeah.
And then this one will be 0, 0, 2, 0, 6, blah, blah, blah.
Yeah.
So you keep this one, add another, try to see if it is in the range, if not, remove it, blah, blah, blah. And repeat this until you have exactly the binary number in the range. The final question is, how do we know that we have come to the last iteration, that we have exhausted all of the required bits of the message? We know it based on the probability of the whole message. So we have to compute what is the probability of the message. And I do it on the encoder side. So I know what is the sequence, I know what is the message, in our case, CAEE $. And the probability of message is simply a product of probability of individual letters, of individual symbols. So I have to simply take 0.3 times 0.3 times 0, sorry. I have to write it down. So the first letter was C, A, E, and $. And they have probabilities. C is 0.2, A is 0.2, E is 0.3, again E is 0.3, and the final $. Is 0.1. And I simply take the product of these probabilities of the observed message, and this product will give me the value of how much? This product would be equal to 0, 0, 0, 36. 0, 0, 0, 36. Okay? So that is the probability of the whole message. And now that I have this probability, I have to compute what is the binary length of such message. So if I would do the binary coding, I simply take the logarithm of this product, logarithm base 2 of this product of probabilities PE for symbols in sequence. Okay, in sequence. And I get the value, in our case, this value is 11, so negative logarithm, sorry, negative logarithm, and 11.44 bits. Then I have to take the first larger integer, because the message must be of the integer length. So after getting this 11.44, I take the first larger integer value, and that is 12. So I know that the message should be 12 bits in length. And this message, this number, there will always be a 12-bit number, fractional number, in the range that I have selected. In any range, it's very important just to stress this. So, for example, I know that this is the probability of the whole message. Now, if I take the total probability 1, 0 to 1, and I take any value x here, and I take x plus this probability of message, Pm. Okay? This interval is, of course, its width is Pm. And then for any x, there exists b fractional number in this b, now I have to select another letter. L, let's say L bits length, in length. That is in the interval from x to x plus this Pm. I can take any value x, and there will always be at least one such binary number, binary fractional number that will fall into this interval. Just due to this taking the first greater integer. So ideally, let's say, if I would have this L, this number of bits as a real number, then it is always only 1. But if I take the first larger integer, sometimes I will have two potential fractional numbers falling into this interval. Because this interval is, of course, slightly larger than the one defined by the 12 bits. So the 12 bits is a stronger, let's say, bound. And for that reason, the actual interval bit is always slightly wider than this value probability of 12-bit number, let's say. Okay? And for that reason, this algorithm works, and you could get actually two potential candidates for some intervals. For some intervals, it will be only one binary number, fractional, falling exactly in the desired interval, and for some interval, it will be two numbers. Any of those two can be used. You take first the lower number, and it's okay. Okay? So the idea is that it's written here. So the reason why we have introduced this dollar sign is just to terminate this decoding process. Otherwise, the decoder doesn't know how long he has to subtract, divide. So now he knows that as soon as he gets the symbol dollar, it means it is the end of the string, the end of the message. But as is the case for the Huffman coding, both algorithms of entropy coding have the problem with errors in transmission. So if for some reason any bit of the encoded message is toggled due to some transfer, let's say, error, transmission error, the decoded message is completely corrupted, let's say. For example, let's say that this is the message that I have received. The original message had 010101 and finally 0000. But maybe the last bit of the message was toggled. The least significant bit of this message was toggled, and the real number, fractional binary number corresponding to this binary representation, is not the one that I is supposed to use. This one is the correct one, but it is the wrong one. So now I will use the same decoding principle and try to decode this value. I will try to decode this value. I start from the wrong value, okay, C, A, E, but the fourth letter in the sequence is wrongly decoded, not as C, A, E, E dollar, but C, A, E, F. A, E, B, E, A dollar, finally. So the message is completely wrong. It is of the completely wrong length, of course. The original message was only C, A, E, E dollar, only 5 symbols. Now I have almost twice that symbols decoded. So obviously, only one bit error in transmission can cause catastrophic decoding failure.
Can we eliminate the extra bits or not?
Can you eliminate
The extra letters.
the extra letters?
Yeah.
That is one clever idea, because you
Yeah,
know
how?
how. The idea is that actually the length of the sent message defines how many letters there could be on the decoded side.
Yeah, we said there would be only 5, right?
Based on the probabilities.
Yeah.
Based on the probabilities. Because you know that if you have received only 12 bits of message, then if I multiply the probabilities of these symbols in the sequence, it will be not 12, it will be maybe 24 or whatever, 30 bits. And obviously this is wrong, because you have only 12 bits.
Okay.
So that is the idea. So simply, based on the length of the encoded message, you immediately know something is wrong.
can you eliminate some bits, some extra letters, like the ones you think that you don't need, or not?
Something like that.
Yeah.
Because you start multiplying with probability for this decoded message.
Yeah.
And as soon as you get the probability corresponding to the length of the received message,
You stop.
you stop.
Yeah, so the other are eliminated. Okay.
So probably the last letter is wrong, but you stop.
Yeah, okay.
Because you know that
you don't found the probability that you want.
Yeah.
Okay.
Yeah, because it is simply based that the probability of the message is simply product of probabilities of individual symbols, and you know what you decode, you simply multiply these probabilities, you get what is the current estimate of the probability of the message, and you compare it with the length of the received binary message that actually is the same thing. So as soon as you exceed the length of the received message, you're certain something is wrong. You have to stop and maybe try simply disregard the last letter in the sequence and say, okay, retransmit or whatever. Okay. So, but the same problem is with the Huffman code, because is, for example, if Huffman code, as I showed before, so for example, this letter 001, okay, this is the symbol D. But if for some reason this first bit is not 0, but it is 1, then I follow the root. I follow the tree. So for example, 101. Okay, 1, this is B, only one symbol. So instead of decoding this as symbol D, I will write, okay, this is 1, this is B. And I completely out of sync. Because after this B, I have 0, 1. And this 0, 1 is 0, 1 is C. So they will replace, instead of having the proper symbol D, I will have BC in the sequence. So that is also very problematic with Huffman coding, because based on this random bit error, you get out of sync with the message. You cannot decode the remainder of the message. The whole message gets corrupted. Okay? So for that reason, they also usually introduce some kind of framing, such that only one frame will be corrupted, and then they will resync after this frame. They will know, okay, this was exactly 256 bits, one part of the message, another block. So if something was wrong in this block, maybe part of this block will be corrupted, but the next block will be properly decoded because it doesn't have any bit error. So you have to do some kind of blocking to reduce this propagation of the error to the following symbols in the sequence. Okay? Okay, so that is the arithmetic coding. Now, the final question we have to ask is how much suboptimal is this kind of entropy coding based on arithmetic coding compared to the entropy? So the answer is simply based on comparison of these two values. So this is a probability of message, and this here is the fractional, I would say, or real length of the message. It is 11.44. But I cannot have 11.44 bits, I have to use 12 bits to encode this message. So the suboptimality is exactly 1 bit, but not per symbol, but per message. So for the whole message, the suboptimality compared to the entropy is 1 bit. So I have to increase the message length by 1 bit in order to encode it with this chosen, in our case, 12 bits. So this might be, for example, 11.01, but still I have to use 12 bits. Okay? And that is the main advantage. The main advantage in comparison to the Huffman coding. Okay, that we have described. So both of the encoders, so they are in the category of entropy coders. Compression is achieved by applying a code of variable length in accordance with statistics of individual symbols of the source. So I use these probabilities and I construct the code optimal for such source. And sometimes you also have to transmit a coding table because if, for example, these statistical properties of the source are changing, if they are not completely static, then I have to retransmit a new table, new coding table, new coding tree for the Huffman table, or these new intervals for the arithmetic coder, because the statistics have changed. And that is also one source of the suboptimality, because you have to lose bits for transmission of the coding tables from time to time. But if the statistics is quite stable, then you do it quite seldomly. It is enough to do it at the beginning, and then you transmit a whole message that is compressed quite a lot. And it works only if the probabilities are different for individual symbols. It doesn't have any gain if probabilities are equal. So, for example, if I have a trivial example, if I have 4 symbols, and if probability is equal to 1 over 4 for every symbol, then the entropy is simply sum of pi of 2 pi, and this is 1/4 times 2 as a negative number, and sub for I to 1 to 4. What I get? I get 2 bits. So the entropy is 2 bits if I have 4 symbols of equal probability, 1/4. Okay, and finally, this is a simple binary code. So if I use the binary code, I will exactly have 2 bits per symbol. So 0, 0, 0, 1, 1, 0, and 1, 1. I cannot do better than that. So this simple binary coding is completely exactly on the bound, exactly on the entropy bound, if the probabilities of all the symbols are the same. But for example, when you have the case that the number of symbols is not a integer power of 2, we don't have 4 or 8 or 16 symbols, maybe we have 5 symbols. In this case, I could gain based on arithmetic coding, because in this case, I cannot use with this kind of binary code, I have to use 3 bits for 5 symbols. I cannot do better than that. Maybe with Huffman, I could do something more clever, but nevertheless, it is again larger than 2, definitely, but less than 3. Okay, and with arithmetic coding, if I code the whole message with a number, then I have interval from 0 to 1, subdivided in 5 regions, equal probability, 0 to 0.2, 2.02 to 0.4, blah, blah, blah. And I have this number based on the sequence that you set. And this way you save bits, because you can get this fractional bit length for the per symbol. And that is not possible with Huffman code. With Huffman code, you can have only integer symbol length, integer length of the encoded symbol. With arithmetic coding, you can have this fractional, whatever number for the length of the individual symbol encoded in the message. Because you encode the whole message with integer number of bits. So divided the number of symbols, you get some fractional number. Okay? In the midterm exam, we'll have problems with both of these encoders, decoders. So, for example, you would have, okay, so anaconda, for example, is a snake, and then you would have to compute what is the probability of individual symbols. So how many symbols do I have? What are the probabilities? Construct a Huffman tree. Based on the Huffman tree, encode this message with the least possible numbers of bits. Okay, based on the Huffman tree. Or maybe the other way, try to construct arithmetic coder corresponding intervals for each of the letters, and encode this word based on arithmetic coder, select one number in the range, encoding the whole message, blah, blah, blah. Or maybe the problem would be to decode the message. Okay, the coding table is this is the number for it to decoder, decode this message. Okay, or maybe it's binary sequence for the Huffman coder, decode this binary sequence based on the tree. So these are typical examples that you have. Or maybe you would have, okay, select your first name or your last name, and then it's a random process that you are trying to model. Okay, construct the arithmetic coder that will be the best optimal for your first name or last name. Okay? Now we go further, but it will be after the break. Maybe before the break, if you have any questions regarding this part. For the arithmetic and for the Huffman coder. So this is quite some simple things, I would say, but they're quite effective. Both of them. And the only problem with this arithmetic coder was it was protected by some patents. So for that reason, it was not completely open for usage. As simple as it was, if you use this idea, you potentially infringing on intellectual properties of these guys. IBM was behind it. Of course, IBM is a big corporation. If you don't want to fight with lawyers, IBM. But this Huffman coding was completely fake. Okay, we have a break now. It is 5 minutes after 5, so we start in 20. So now we will try to combine these two subjects that we have covered. So first subject is the quantization and quality, or let's say distortion, let's say, introduced by the quantization. So what is this signal to quantization noise ratio? We have shown it depends on the quantizer, on the number of bits, and so on. And on the other side, we have the entropy. So we have to transmit this message to the other side. We have the output codes at the output of the AD converter. We encode them somehow efficiently using entropy coder, and we have the coded message. And the final issue is then what is this relationship between the length of this encoded message and the quality of the signal that is represented by this message. Okay, so this is the subject that we can name entropy and quality. So the problem description. So we have some kind of amplitude continuous time discrete process that we want to encode for the purposes of compression. So this is some process X, and this is X real valued process. Okay? That is our input. It might be, for example, time signal, but it doesn't have to be time signal, doesn't matter. So this is then forwarded to the AD conversion that does the quantization. And normally this will be time discrete process. So we have X of n as a sequence of numbers of real valued numbers. So the sampling is done already here, or as a part of AD conversion. It doesn't matter. But now we have this X hat of n, and that is the quantized value of this signal value, of the ideal signal value. And of course, we have some kind of error here. So this is error signal. This number sequence that is at the output of AD converter can be entropy coded, entropy coder. So we have a binary message. 1, 0, 1, 1, 1, 1, 1. And we have some rate here as a bits per symbol or bits per message, whatever. We have some rate, transmission rate, or the channel to transmit this sequence of numbers. The entropy decoder reconstructs perfectly entropy decoder it perfectly reconstructs this encoded message if you don't have any bit error during transmission. And what you get after this decoding is exactly the same sequence of numbers that you have in the output of AD converter. So of course, if I have DA conversion here, I would have exactly the quantized, analog quantized representation of this signal. And this reconstructed message, this Y, for example, Y hat, is the same as X, because if you don't have any errors in transmission, you should have perfectly reconstructed signal and output of DA converter. You might have also some interpolation here, so as a part of DA conversion, such that you, after interpolation, end up with Y of t. And this Y of t is corresponding to original X of t. So continuous signal X of t is sampled, then I have the sequence X of n. This sequence is then converted to the sequence of numbers, quantized numbers, X hat. This X hat is of course different than X, and that is the source of our error, quantization error. And the rate required to transmit the sequence of numbers X hat depends on the entropy of this X hat of n. So I know what are the probabilities of all the symbols. For example, this X hat of n might be quantized as symbols for -3, -2, -1, 0, 1, 2, 3. So these might be the possible symbols at the output of the AD converter. We only have 7 symbols. And then if I know the probability, what is the probability of -3, probability of -2, blah, 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 I can easily compute what is the entropy, H of S, what is the entropy of this source that enters the entropy coder. If I know the entropy, I can construct the entropy codes to approach this value with the average bit rate for the general rate. And this suboptimality would be either 1 bit per symbol if I use the Huffman tree coding, or 1 bit per message if I use the arithmetic coding. Okay? But in the case of there are no losses in the transmission, on the decoder side, I would get exactly the same message here. This Y hat of n would be the same as X hat of n. I can easily reconstruct this with Y hat of t, but more or less all of this is transparent. So the only error is introduced in this part AD and DA. So due to sampling, time sampling, as we have shown. So time sampling introduces this problem of aliasing. So if you don't have band-limited spectrum of the input signal, then this aliasing and error can happen. So that is one source of the error due to sampling. And the another source of the error is due to quantization, because I use a finite number of quantization levels. So I have either granular error due to this step size, but I also have this overload error. If I exceed the range, dynamic range of the converter, if the input value is less than the least allowed value or above the greatest value, then I have this clipping and I have large error, of course. Okay, now it says here we transform this amplitude continuous process, this X of n, which is a real value process. We now transform it into discrete process, but not only discrete in time, but also discrete in value. Because we have only, for example, in our case, 7 symbols allowed for representation of this X hat of n. So only these symbols are allowed. Of course, the entropy here is definitely less than 3, because if we have 7 symbols, logarithm base 2 of 7 is something below 3. If I would have 8 symbols, it is 3, if all the probabilities are the same. It cannot be larger than 3. that I want to say. So the entropy of a source with 8 symbols, it cannot be larger than 3. So because it is the case when I have the binary code. So if I assign a simple binary code to this to the source, I would have exactly 3 bits for 8 symbols. But obviously the entropy is lower than that if the probabilities are not equal, okay, and especially the number of symbols not power of 2, integer power of 2. Okay, so I want to apply the entropy coder in order to achieve compression. So this entropy coder is here to achieve the compression. And what I want to relate this rate here, what is the rate, expressed as a number of bits per symbol, in comparison to the error, SQNR, signal to quantization noise ratio, SQNR. So I measure the variance of this error, and I compare this variance in a ratio to the variance of the signal. I convert it to the logarithm scale by taking the logarithm base 10 of this ratio, 10 times that, and I get the SQNR. And I want to relate this SQNR here to rate here. That is my question. How these two relate? That will be the main topic of this section. Okay. There are two possibilities how we can construct such a system. One would be entropy constraint. It means that, for example, our channel has the highest possible transmission rate. For example, our channel has the highest rate 3 bits per symbol. I cannot transmit more than 3 bits per symbol because it is a capacity of the channel. In this case, I have to adjust the quantizer together with the entropy coder not to exceed this value, this bound. So the entropy is bounded due to the channel limitation, and I have to design the system in a way that the output entropy and the output of this entropy coder is less than the channel capacity. So that is the first way, it is entropy constrained. And what I get. So the quality is, of course, dependent on the capacity. If I have low capacity here, low transmission rate, I have to increase the step size on the quantizer to reduce the rate. Because if I increase the step size, automatically the entropy of this x hat of n is lower. I have a smaller number of individual symbols because the step size is large, and I don't have, for example, -3 to +3. I have maybe only -1, 0, and 1 because the step size is twice, and I have only 3 symbols, not 7. So that is one way how I can affect directly the entropy and the output of AD converter.
So it depends on the step size at the time.
It depends on the step size. So the step size that directly affects the output entropy, it is a trivial way how I can control the entropy. By simply increasing the step size, I will reduce the entropy. But of course, the price I have to pay is the lower quality. So if I increase the step size 2 times, I lose 6 dB in quality due to twice larger step size. The other way would be distortion constraint. That somebody told you that the distortion must be less than something. Okay, so for example, it is required that this signal is transmitted with at least 30 dB SQNR. And in this case, if you have this distortion, you have this quality constraint. This must be better than some bound, 30 dB. Based on that, you have to decide again the step size. What is the required minimum step size to achieve such quality? So we have shown that by simply varying the number of bits, we can go along this curve, SQNR curve, and decide how many bits we have to use to achieve desired SQNR. But now that we have this delta, this step size, now we construct the entropy coder for such source, and the rate we get, it is such. We cannot go less than that. So the channel capacity must be greater than the rate we gave in the output of entropy coder. So that is the distortion constraint. The reconstructed signal must have the error less than some prescribed one, and we have to design the quantizer to satisfy this requirement. Okay. So the answers how to design this such coding system based on either entropy constraint or based on distortion constraint, the answer is given by the information theory, and one particular branch of this information theory is related to source coding. So source coding gives us the answer, and one particular, I would say, theory of this information theory that deals with the study of the relationship between the rate and the quality, rate and the error, or rate and the quality, is this so-called rate distortion theory. It is called rate distortion theory. This rate distortion theory was introduced by some fundamental work by two guys, or by at least Claude Shannon. Claude Shannon, he was working at that time for Bell Laboratory. And it was almost 80 years ago, 75 years ago, when he devised this theory. Okay, practically all modern encoders of media signals intensively use the knowledge from this information theory. So they apply this information theory in practice. And in our course, since we have the limited number of hours we can dedicate to this topic, we will introduce the simplest version of this entropy-based coding. It is called entropy-constrained scalar quantization. Entropy-constrained scalar quantization, or the abbreviation is ECSQ. ECSQ. It follows exactly the diagram I have shown on the whiteboard. So the idea is, I have a scalar quantizer, so the input signal is a scalar signal only. It is not a vector. Sometimes it is much more effective to encode the signal as a vector. But in our case, we have individual scalar values for each time sample or whatever. So we have a scalar source, and this scalar source is then quantized with a simple PCM quantizer as we have described before. At the output we have numbers, integer numbers. And these integer numbers are treated as an output of some random source, random discrete source. For each possible output symbol, we have corresponding probability. We can count how many times the value -3 was observed, how many times value -2, blah, blah, blah. So for such source, we can easily construct the best possible entropy coder, okay? And this simplest form of entropy constraint quantization is actually applied in audio coding, in audio signal encoding. For example, these popular standards for audio encoding are mostly based on this entropy constraint scalar quantization. Great efficiency is achieved if the sequences are longer and statistically independent, or at least uncorrelated. So usually you have some pre-processing that does this decorrelation. So these linear dependencies are somehow modeled or resolved with this pre-processing that captures the correlations between individual samples of the signal. So if there are any correlations, they will be modeled with this pre-processing part, and for that reason I can easily remove them. If I have estimated the model of this correlation, I can decorrelate them. And once these samples are decorrelated, the simplest way would be to simply quantize them using entropy constraint scalar quantization. So I have sequence of numbers, real numbers, and the output of this pre-processing decorrelation step, and this sequence is then simply quantized with this entropy constraint ECSQ. Okay. In your laboratory exercise, in your first exercise, you would use this technique to encode speech signal. So you will record one short speech signal, and you will try to quantize this signal directly in time domain using the concept given so far. So linear quantization, BCM, constructing entropy code, doing the entropy coding, computing the rate, distortion, blah, blah. But for the whole laboratory exercise, you would also do the transform coding. And that means you would take not individual samples of this signal, but you would take a block of these samples. For example, 4 neighboring signal samples. And you would treat this as a vector of length 4 and apply block transform to create another vector of the same length using transformation metrics. So in your case, you would have a sequence of values xn, xn plus 1, blah, 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 maybe xn plus 3. And this here will be treated as a vector. So I will simply construct a vector by taking these values. That would be the vector x, as, for example, as a vector, just to emphasize it as a vector. And then you will compute another vector y as a matrix multiplication of this m and x. And this m would be transformation matrix. So instead of using scalar quantizer to quantize individual values in this sequence, x of n, x plus 1, blah, blah, you would first transform this vector into another vector, and you would design a new quantizer for each individual elements of this y vector. So if I visualize this y vector for the first block of 4 samples, so for example 0 to 3, then another y for 4 to 7. Okay, so I have a sequence of transform vectors, 8, 11, blah, blah. Okay, I have a sequence of 4-dimensional vectors. And now what I do, you have to construct a scalar quantizer for the first coefficient of this vector. So these are spectrum coefficients. So after applying this transform matrix, what you get is a spectral representation of this signal. Trivial spectral representation, but nevertheless spectral representation. We only have 4 spectral coefficients. In your case, you would use discrete cosine transform matrix. So this matrix here would be discrete cosine transform, DCT matrix. It is simple orthonormal matrix. It means that its inverse is equal to the transpose version of the matrix. So this m to the minus 1 is actually m transpose. And what is also the advantage? All the values in M are real numbers. That is the main difference to the Fourier transform matrix, because it has complex numbers as a transform matrix. But discrete cosine transform has the advantage that all the elements of M are real numbers. So you have the real vector x multiplied with this matrix, you have a real vector y. Okay? And now you have to construct 4 individual quantizers for each of the rows. Okay? So what I get, I would get a quantized version of this sequence y. So it was the first vector quantized, second vector quantized, blah, blah, third vector. Okay? So that is based on quantization, so Q. For example, for the first row, I have a quantizer designed to operate very good on the first row of this process. And then I do the encoding, entropy-based encoding for each of the rows. Like I have 4 sources. I don't have only single source, as it was before, x, sequence of values. Now I have 4 individual sources, but their rate are 4 times lower than the original rate. because I have this blocking. I take 4 samples, 4 samples, 4 samples. So the rate of each individual row is 4 times lower than the original rate. But I have 4 sources, not only one. Okay? Now I do the entropy coding, decoding, and reconstruction. So with reconstruction, the only thing I have to do, this y hat must be multiplied with the inverse matrix. And I will get the x hat. So on the decoding side, I simply collect these vectors, and each individual vector is then transformed to corresponding x vector by simply having m transpose times y hat, and it gives me x hat. And then by taking out these individual elements of this x hat, I get 4 samples of the reconstructed signals. First row, second row, blah, blah. I have 4 values at the output. So that is the way that you will do your laboratory exercise. So you will apply this knowledge that I will show you right now to quantize not only one source, scalar source, but actually 4 sources. And these sources, the main potential for gain is that individual rows, they don't have the same values. So that is the basic idea. Why do you do it? Because it is actually just computation for something. You have to gain something. You have to multiply this, take the inverse, blah, 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 and do this 4 times instead of only 1 times. What do you gain? You gain the rate, you gain the final compression, I would say. You achieve the compression. Why? Because typically the variance of the first row is the highest. It is the smallest component of the spectrum, the smallest varying component of the spectrum. Then as you go further, the last row represents the highest frequency of the signal. And typically our real-world signals have tendency to be low-frequency signals. High-frequency components are much more interesting, I would say, in the real world than the low-frequency signals. And in this way, if the signal doesn't have high-frequency component, then this first row is more or less sufficient to completely describe the slow variation of this source. So if I would simply replace the last row with zeros, I would remove the highest frequency from the signal. And probably this last row wouldn't result in great loss in perceptual quality. Because the energy of this row is small, the original part of the spectrum, this part of the spectrum was of low energy, and if I completely replace this with 0, I wouldn't lose much. So that is the basic idea of transform coding. This that I have described is the idea of transform coding. I do the coding in transformation domain. So I first take the sequence of numbers, convert it into spectral domain, and in spectral domain I do the quantization. This y is converted to y hat. It is transmitted to the receiving side, and it is decoded and inverse transformed to the original domain, x hat domain. And the gain is achieved. Why? Because the variance of individual channels is not the same. If the variance is the same, there is no gain. It is the same as if you would use the quantization in original domain. You don't have any improvement in the quantization quality regarding the rate. But if the variances are different, then you can gain. You can achieve, it is called transform gain, because it is based on transformation. So transform gain can be achieved if the variances are not equal. Okay. This is a short introduction to your first laboratory exercises regarding the application of this transform coding. Then, just to show you the idea, so the input to the encoding process is digitized media signal of nominal accuracy. And let's say that after this, I will introduce this AD converter that will reduce the number of levels just to reduce the entropy. So let's say this nominal accuracy is like a real number, like an infinite accuracy. And after that, I will apply the AD conversion just to reduce the entropy, of course, by introducing the error. So if I have a large step size, I will introduce a large SNR. Low SNR value, large error, okay? But nevertheless, I will have much more entropy if the delta is large, okay? So the input resolution is much higher than the resolution of this entropy constrained scalar quantizer that is used in the context of compression. And typically we would use signed representation. So let's say that it is normalized to plus minus 1, and it corresponds to the range of blah blah minus 128 to 127 for the 7-bit case. Okay, but now we will start from the very simple example of only 5 quantization levels. So let's suppose that we have this range of input signal, minus 1 to 1, and it is subdivided into 5 equal ranges of width 0.4. Why? Because, for example, this range, minus 1 to minus 0.6, it will be encoded with value, with symbol, minus 2, and the centroid corresponding to this range is minus 0.8, the center of the range. So the central value from the range is the representative of the whole range. It may be better to show it this way. So this is minus 1 plus 1. I have only 5 levels, quantization levels. So the whole range from minus 1 to minus 0.6 is represented as minus 0.8. Then from minus 0.6 to minus 0.2 as minus 0.4. I have equal widths of all the 5 levels, all the 5 intervals. Okay? And the representative value is the center of this range. So this C is a class. C minus 2 means that it is class corresponding to symbol minus 2. It means that the signal value is somewhere between minus 1 and minus 0.6. Okay? So we could easily compute the probability for all 5 output symbols. For symbol minus 2, minus 1, blah, blah. So we can find the entropy of such shorts. Okay? We will first assume that this quantization is exactly uniform, that we have uniform step size. Delta is equal for all the intervals. Because there are different quantizers and they have non-uniform step size. You could also design a quantizer that doesn't have to have exactly the same step size for the output symbols. It was in the past when they had to design a rate constraint quantizer, so they have only 3 bits. So they have 2 to the power 3 bits at the output of AD. So the question was how to arrange the quantization levels to have the least distortion given the probability density function of the source. So you know the PDF of the source, and you ask yourself, how should you arrange the quantization levels for these 8 symbols to have the least distortion? Okay? And the answer is obviously if this is the PDF. So fx of x. It has some form. Okay. Obviously, you have to put the quantization levels to the values that are often in the signal, that are often occurring in the signal. And these are these here. So the density around here should be greater to represent these often occurring values. While the density here might be low. Okay? So you can displace the quantization levels at the positions where we don't have any actual values, where the probability of such values are very low. Okay, so they would have non-uniform quantization, okay, levels. So this delta is not the same. This is delta 1, this is delta 2, okay, delta 3. So if the number of quantization level is a constraint, and if we have to select which are the optimal values to represent this random value process, then I will probably construct something like this. Okay, this range here would be represented with this value. Okay, then this range here with this value, and so on. So for each of those ranges, you would have a different symbol with this value. And then the idea is how to find the optimal thresholds, optimal boundaries, to have the least distortion given the PDF. Okay? That is one way how to construct the quantizer if you have constrained number of output levels, output symbol. But if the number of output symbol is unconstrained, then I can rely on the entropy coder to reduce the rate. And I simply say, okay, I will use the uniform quantization with the step size that are equal, and I will rely on the entropy coder that codes that are symbols that are very of low probability would automatically be encoded with a long code, while the often occurring values will be encoded with short code. And I would get the average code that is still low. But if you have only 3 bits without any entropy coding in the output, then you have to carefully select the values for these 8 levels to have the least distortion for the output fixed bit rate of 3 bits per symbol. Okay? So this is the two ways you can design the quantizer. Either by constraining the number of bits, output bits, per symbol, it must be 3, then arrange the quantization levels non-uniformly based on the PDF of the signal. Or the other way that we will use is use always uniform scalar quantization with the same step size for all the values, and then rely on the entropy coder to reduce the rate. Okay? So it shows here this dashed line is the real value, the unquantized value of the input signal from -1 to +1. And the red line represents the quantized value. So this whole range from -1 to -0.6 is represented as -0.8. Then -0.4, then 0, again +0.4, +0.8. And if I subtract this blue line and the red line, I get the quantization error, like a sawtooth signal. Do I have it? Quantization error, okay? Plus minus half of the step size is the error. Okay. Now I have to compute what is the expected value of variance of the quantization. So this is the error. But for each of those errors, I have to know the probability. What is the probability of this value, blue value? So how often does this value -0.9 occurs, for example? Because for -0.9, the error would be this. So I have to compute the expected variance of the quantization error based on the PDF of the signal and based on the distortion equation that defines this value, what is the error for each input value. So for each input value, I can compute what is the error due to quantization. And we will do it exactly this way. So I will try to compute the expected variance of the quantization error as based on the PDF of the input process. So I will start from fx of x, and I will try to compute distortion d as the expected value of e squared, error squared. Okay? So this d here is simply this x minus delta times I, because this is a quantized value. it is simply integer number times step size. This was based on rounding. I take the first integer number to represent this real value, and if I remove this x hat, I get the error. I square the error. I square the error to get the variance. The expected value is 0, bias is 0, because I have symmetric distribution around 0. I don't have to subtract this minus expectation of A, E. Okay? Because normally, if I have to compute the variance, I always have to subtract the so sigma E squared is the expectation of E minus expectation of E squared. And what I take as a 0 is this here. So this expected value of error is 0 because I always have a symmetrical distribution of the error minus half step size plus half step size. Where do I have it? Let's follow the presentation, but now we'll have to do the break. Now it is exactly 6 o'clock, so after the break we will do the derivation of theoretical part. Okay. If you have any question, prepare them during the break, and then after the break we will continue. Okay, so first of all, what we will compute for this signal, we will compute what is the entropy at the output of this AD converter, but we will assume that the signal PDF is uniform. The simplest form of PDF would be uniform PDF of the input signal. So this fx of x would look something like this. So the input value of the signal is from -1 to +1 with equal probability. And obviously, this must be 1/2 in order to integral to be 1. In our case, what we have to do, we have 5 output symbols. -2, -1, 0, 1, and 2. These 5 output symbols, they are corresponding to the range, equally divided range of 5 possible values, I would say. So class -2, class -1, class 0, class 1, and class 2. Since the PDF of the signal is uniform, then the probability of each of those classes is equal. So this probability of class, so probability that x is element of class -2 is equal to 1/5. And the same for any other class. The same for any other class. X element class I from -2 to +2. So the probability for each of these potential symbols is 1/5. 1/5. This 1/5 is the integral of this PDF in the range from the lower bound to the upper bound. Okay. And now we can compute the entropy. So the probability of -2 is 1/5, logarithm of 1/5 plus, and of course negative logarithm. It is extracted in front of the parenthesis. So, and after repeating for all the symbols, what I get is the entropy of the source. So the probability of, for example, class 0 is simply integral of PDF in the range for the class 0. Class 0 is from 0.2 minus to 0.2 plus. So if I take the integral, that is then simply the integral of a constant. Constant is 1/5 in the range of 1/5 to plus 1/5. Okay? And what we get is actually 1/n is the probability, as we have expected, because all the intervals have the same width, and the probability of all the values is equal for x element, this interval, and then in our case, we can easily compute the entropy. Entropy is then 2.32 bits. Since we know the probability for each of the intervals is equal, 1/n, this is this uniform probability of the source. In our case, this n is chosen as 5, and the step size is 0.4. So this is 0.4 times 5, that's 1/2. So the density is 1/2, and if we integrate this 1/2 in the range, for example, minus 0.2 to plus 0.2, we will get the probability of 1/5 for the interval 0, but it is the same for all other intervals, -2, -1, 1, and 2. And so we get the entropy of 2.32, what is expected. If I would have 8 levels, uniform levels, this would be 3 bits. Okay, if there is only 4 levels, it will be 2 bits. So it is above 2 bits and less than 3 bits. If we express the entropy in dots, then instead of using the logarithm base 2, I would use the natural logarithm. So this is the logarithm base 2. And you always have to remember that, for example, if your calculator doesn't have the logarithm base 2, if it only has, for example, logarithm base 10, then this logarithm base 10 of x, if I divide this with logarithm base 10 of 2, I will get the logarithm base 2 of x. So it's a simple trick. So to convert the base of the logarithm, you take the logarithm that you have, logarithm 10 of the value, and divide this with the logarithm 10 of 2, and you will get the logarithm base 2 of x. Okay? Going further, so this is the part that we have computed the entropy. The entropy is this value because all the probabilities are equal, and if I introduce this into the expression for entropy, I would get this value of 2.32 bits. Now I will continue with the distortion. So what is the expected distortion if the input process is uniform, and if I quantize this process with 5 levels? So of course the distortion is the expected value of difference between x and x quantized, okay, squared. Now I have to say what is the x quantized. So the x quantized is decided based on this equation. I simply divide the real value x with the step size. I take the nearest integer, and after that I simply multiply this integer with the step size, and I get the linear PCM quantized value corresponding to this code, this integer code, hidden behind this quantized value. So I have to substitute this here. But actually, this integral can be computed for the whole range x, but also can be computed by simply combining individual intervals. Because this integral here is from -1 to 1, but I can also compute this integral in individual classes by simply going, for example, from -1 to -0.6, from -0.6 to -0.2, blah, blah, blah. So by simply dividing this integral into these 5 classes that correspond to our quantizer, why do I do it? Because in this case, this xqi is constant value. Because for the first class, class -2, this value is -0.8. So in this case, I can easily compute what is the difference between x and xqi. Okay? So I simply divide this whole range from -1 to 1 into 5 individual ranges, and I sum up this for all the symbols, so -2, -1, up to +2. Okay? And now I have to find what is this. I have to compute what is this. I know that this is 1/2. So then the density of the input process is 1/2. I have to find what is this value here for one chosen I. For one chosen interval I, what is the value of this part in the brackets? Okay. So I have sum 1 over delta n. This is this probability of the source, 1/2 in our case, because delta is 0.4 and n is 5. Then I have the interval. The lower bound is delta I minus half step size. The upper bound is delta times I plus half the step size. For example, for the first class, this I would be -2. So it is -2 times 0.4, it is -0.8. And minus half of the step size, so it is -1. So -0.8, again -0.2, altogether it is -1. And the upper bound is -0.8 plus 0.2, so it is -0.6. So the range for the first integral is -1 to -0.6. Then this is the x, the real value, and this is the quantized value. This quantized value is always step size times this integer I. For the first interval, this integer I is equal to -2. Okay? And then I have to integrate this. But before I integrate, I will introduce a substitution. So I will introduce this x prime is what? This x prime would be exactly the argument in the brackets x minus delta I. Because in this case, this here is x prime. Okay, and in this case, if I want to find the new bounds for the integral, if the original bounds in x are this delta I times delta times I minus delta half, then in x prime would be lower bound. I have to remove delta I. So what I get simply minus delta half as a lower bound for the integral, and the upper bound is again plus delta half. So in the variable x prime, the bounds are always the same for all I. So because this delta times I is cancelled by this substitution. Okay, so this is trivial. I have new bounds for the integral, minus half step size or plus step size. This here is x prime squared. I only have to check what is the dx prime. If there is any change to this differential. Of course, if I take the derivative of this, dx prime is the same as dx, because this is a constant. So if I take the derivative, this constant vanishes, and of course this dx prime is the same as dx. So I can simply write this dx prime here as equal to this one. And this integral here is a trivial integral that you know. It is simply x prime to the power of 3 over 3, and after substituting the values for the lower bound and upper bound, and after simplifying this expression, I will get the expected answer that we have already derived before. So what is the distortion of the uniform quantizer? The distortion of the uniform quantizer is exactly delta squared over 12. Exactly as before. Why? Because our quantizer has equal step sizes, and probability of each of the classes is identical. So this fx of x that was in front of the expression is a constant value. So we could extract it out of the integral. But it doesn't have to be constant. So for some other examples, this fx of x might be some whatever, pixel linear whatever function. In this case, you cannot extract it out of the integral. You have to integrate it together with the error. So you have some function that you have to integrate along this range corresponding to one of the class, and add up to this for all of the classes. Okay? But in our trivial example, since our fx of x is uniform, is a constant, I can extract it in front of the integral, and I can easily compute the integral of only this part, and I get the answer as before, as we have derived for the case of uniform quantization. Now that I know the distortion introduced by the quantization, I also have to find the variance of the signal, because I have to compute the ratio. Signal variance over error variance, 10 log 10. Okay? And the same as before, to find the variance of the signal, it is expected value of x minus expectation of x squared. And then, since this expectation of x is 0, because I have a symmetrical PDF around center point 0, then I can omit this part. I have only expectation of x squared. And according to definition of expectation, it is simply x squared times the PDF dx over the range of the signal. As before, if I integrate this, this is a constant, I can extract it in front of the integral, 1 over delta n, and I have this trivial integral of x squared in the range minus delta n half to delta n half. Why? Because this value here is the dynamic range of the converter, -1 to +1. So the whole range is then integrated, and what I get is delta n squared over 12. Okay? And now I have the variance of the signal as well as variance of the distortion of the error, and I can compute the ratio. What is the ratio of the sigma x squared compared to the distortion d, which is actually this e squared. Okay? So 10 times logarithm base 10 of signal variance in relationship to distortion d. Okay? After substituting this pair of values into this expression, what I get is simply 20 times logarithm 10 of m. Very trivial expression. So this 20 comes due to this squared. So if you extract this squared value in front of the logarithm, it is 2 times logarithm. Okay, so it is 2 times 10, 20 times logarithm 10 of n. So this is the distortion if the quantizer has n levels. And finally, I want to relate what? I want to relate this SQNR with the entropy. With the entropy that we have derived here, h of I. And this h of I was simply logarithm, in our case, this entropy of the source was some negative sum pi log 2 of pi for I. And since we had the equal probability, it is simply 1/5 times logarithm base 2, let's say of 5, because it is negative logarithm of 5, and then multiplied 5 times, because it is the same for all intervals. So this part here is for one element of the sum. Okay, 1/5 logarithm base 2 of 5, because you cancel out with this minus, and times 5, and I get the logarithm base 2 of 5, and that is n. So in our trivial case, the entropy of the source that has 5 symbols of equal probability is simply logarithm base 2 of number of symbols. Logarithm base 2 of n. Okay. And I want to then derive a relationship between h of s, which is logarithm base 2 of n, and the other is distortion. Distortion that we have just computed. Distortion is SQNR, SQNR, for the same case is 20 log base 10 of n. Okay? Now I can, for example, express this n here as 2 to the h of s to simplify. Solution. So this number of levels is entropy to the power of 2. Okay? And if I introduce it here, so this is then 20 logarithm base 10 of 2 to the power of hs. And of course I can extract it in front of this. So it is 20 logarithm base 10 of 2, but times h of s. Okay? So this exponent is extracted in front of the logarithm. So 20 times h of s, logarithm base 10 of 2. And we know that this part here is this 6.02 decibels. So we get that this S2NR in our case is simply 6.02 times entropy expressed in decibels. So I can derive this relationship between the quality measured and the rate and the output rate. So that for each bit that I add to the output rate, I get 6 dB of quality. I have this linear relationship. Okay? If I introduce one additional bit to the channel, if the message is not 3 bits but 4 bits per symbol, I gain 6 dB in quality, 6.02 decibels in quality. Okay, so that is a very simple example just to show the theory behind. So the entropy expressed in bits and quantization distortion expressed in these decibels, these two are linearly related by simple constant factor 6.02. Furthermore, to reduce the distortion by 6 decibels, I have to increase the output entropy by 1 bit. Since our distribution PDF of the input process is uniform, the entropy encoder does not achieve compression with variable length code because all codes are of equal probability. So ideally, all the lengths should be equal. But for some other example, if the PDF is non-uniform, if some symbols are occurring much more often than the others, then of course these oftenly occurring symbols will have shorter code. And these seldomly occurring symbols will have a longer code. And then I will achieve compression. The output entropy of any input process must be lower than this uniform. So this is the worst case, I would say. The uniform distribution of the source is, of course, the worst case because I don't have any gain due to this entropy coding. Okay, but for arbitrary fx of x, we have to determine the error by summing individual expected distortions for each of the integrals. Because for each of the integrals, this extraction of the PDF, this here, I cannot extract it in front of the integral as a constant. Because if this fx of x depends on x, I must keep it in the integral and compute the integral together with corresponding probability for that particular interval. And in your problems in the exam, you could have such case, but it would be some simple PDF that can be integrated by hand. So for example, if you don't have uniform PDF, but it is something like piecewise linear or piecewise constant, whatever. So, for example, this fx of x for these 5 intervals might be something like this. linear increasing, constant, decreasing, whatever, constant, and then increasing, whatever like this. So pieces linear. So in this case, you have to write what is the function for this part, and insert corresponding function into the integral for the first class, the second class, compute the integral, and find the expected value of distortion. Okay, for this more complex, I would say, example. Okay. Furthermore, what we have learned that the coding with entropy or distortion constraint, so we can either design quantization system or coding system with entropy constraint by constraint defined by the channel capacity with the transmission rate that is available to us. So I have to compress it in a way that it fits into the channel. So that is one way how we can design the coding system with entropy constraint. Or the other way that we have to design the quantization system based on the distortion constraint. Because we say, okay, distortion must be less than this. In this case, we have to determine step size based on the required distortion, and for the rate, whatever we get, we get. You have to have this capacity, otherwise you cannot transmit the signal without this capacity. Information theory gives us the answer to this question, how to design such a system, this rate distortion theory, and we have focused so far on the example of the most simple quantizer, and that is scalar, entropy constrained scalar quantizer, and we have discussed its applications. Now we will continue with the so-called high rate quality, but today we will only make a short introduction because we have only 15 minutes. So the idea is that how to avoid the problem of integration of fx of x in one class. How to avoid this integration, how to have a simple approximation. So the actual value, for example, when I compute this di for this interval, let's say this I is -2, and I want to find d -2. So distortion corresponding to this range, this first interval. So this distortion is then this integral here, where it is, this here. Okay, so this di is this integral. So for x element c -2, I have to integrate this fx of x times x minus, in our case, plus 2 times delta, okay, squared dx, because this is minus I, so this is plus 2, okay, and I have to substitute this linear function here to find this integral, because in the trivial example, since this was a constant value, I could extract it in front of the integral. But now, if it is a linear value, I have to insert it here, keep it here, find the integral based on this linear function. Okay? I want to avoid this. I want to approximate this based on some simplification. And this simplification would be approximation of this linear function with a constant function. Okay? This is already constant. Again, some constant function here. So I will replace this actual value of PDF in one class with the constant probability for the whole class. And this probability will be computed based on the density of this central value. So fx of x for this central representative value would be taken instead of the original function that depends on x. So instead of using whatever function that is actual in this interval, I will use the central value, the value at this representative point. In our case, this was minus 0.8. This was minus 0.6. So instead of using the actual function, I use the density at this value minus 0.8. And this is, of course, approximation. I will introduce the error due to this simplification by using this constant value instead of the actual curve. But nevertheless, if the number of levels is large, then this stepwise approximation is close. So if the function is whatever function, but if I have many levels, then in this narrow range, this constant approximation is sufficiently close. And that is the basic idea behind high-rate quantization theory. So instead of using the actual PDF in each individual class, I will approximate this PDF with the central PDF in the center of this class. Okay, so it is written here. So instead of using the actual function, actual probability density function for all x's in one class, I will simply take the value, the density at representative value of this class. Okay? And with the described simplification, with described assumption, we can obtain the following solution. We will immediately introduce the solution. We're skipping the derivation. Immediately we'll introduce the solution of the problem. And the answer is, indeed, the quantizer that has uniform spacing of quantization level delta is the best solution for every input process. Because the question was, is it a really uniform scalar quantizer that is the best one? Maybe some other distribution of quantization levels would be better. But if you have the entropy model after quantization, then the answer is, it can be proved that the best possible quantization is uniform scalar quantization, followed by entropy model. And you would get the least rate for the same quality. Okay, to achieve the best rate, the least rate for the desired quality, you would simply use a uniform scalar quantizer with a step size delta, and followed with the entropy model. And you would get the output rate that is the least possible rate for this distortion. So the ratio of the output entropy, h of I, and distortion that is introduced due to quantization with step size delta is given by this expression. Okay, so this here is the entropy of output indices. So this -2, -1, 0. So these are the output indices. What is the entropy of the output symbols? It is equal to something minus 1/2 logarithm base 2 of 12 times distortion. This distortion is directly squared step size divided by 12. Okay, so this is a value that you must know in the middle of the night when I wake you up. So what is the distortion of the uniform quantizer with the step size delta? Oh, okay, it's delta squared over 12. Okay, so this is the distortion, and relationship between the logarithm of this distortion and output entropy. I have one term here, h of x, and this h of x is the only thing that is defined by the signal. So I don't have any signal dependent part here. It only depends on the step size of the quantizer, the chosen step size delta. This is the output rate, and this here, h of x, is the so-called differential entropy on the source. So this differential entropy is something that is defined for continuous valued signals. So the classical definition of the entropy, h of s, is for the discrete process. I have 5 symbols, -2, -1, 0, 1, 2. But what if I have a real valued process? So this x is element of R. So a real valued process. How to find the entropy of such source that has a given PDF, but it is not discrete, it's continuous. So all values of the x are possible. For example, as shown here, linear independent, but nevertheless. So all values in the range -1 to 1 are possible, not only some discrete values. So for such fx of x, I can compute this differential entropy. And definition of this differential entropy is completely analog to the conventional entropy, but instead of sum, I have the integral. So before, it was sum of probability times logarithm probability. Now instead of sum, I have the integral, negative integral. So instead of probability, it is density times logarithm of probability density. So completely analog expression to the case of discrete process. But now instead of having histogram, instead of having individual probabilities for 5 classes, I have PDF for any real number x, where this signal exists. Signal value exists. So fx of x times logarithm fx of x dx. And as such, it is nothing else but, you know that when you multiply some function with the probability, then it is actually expectation of this. So it is nothing else but the expectation of the negative logarithm of density. So the definition of this differential entropy is given here as a negative expectation of the logarithm of PDF. So this part is defined by the signal. It depends on the signal and its statistical properties. So this part here. This part here, it depends only on the quantizer, on the step size. So we have now derived that depending on the signal, the output entropy is either lower or higher. So that is the reason why it is called differential entropy. It doesn't have any absolute meaning. It has only meaning in comparison. This differential entropy can be used only for comparison. So for all processes that have the same variance, which of those has lower or higher differential entropy? And this gives us the answer on the influence of the signal to the output rate, to the output entropy. So if the signal has higher differential entropy, it will cause higher required output entropy for transmission. So this differential entropy is somehow measure of complexity for quantization. So how complex is this signal to be quantized, to be transmitted over the channel? So higher the differential entropy, then higher is the output required rate to achieve the same distortion. So it is very simple measure, and this part here can be easily found because, for example, you have this function here. You simply compute this expression by integrating along 5 regions. Okay, this is a PDF. It is piecewise linear. You divide this integral into 5 subintegrals. You compute what is the total differential entropy for such sorts. And once you have this answer, it is one constant value. So the only thing you have to know is what is this constant value. It is like offset that defines, so what is the offset of rate distortion curve. So if the offset is higher, it means that the required rate is higher to achieve the same quality. Okay? And this would be the final expression that defines this line, signal to causation nodes relative to output entropy. So this is the output entropy, h of I. And as we had in our previous example, I had only this part here, 6.02 decibels, times output entropy. And that was the quality. So 6 decibels times the rate. But now I have one additional term, SQNR 0. So this is the offset of this linear curve. So higher the offset, better the quality. For the same rate, I would achieve higher SQNR if this term is higher. And this term, SQNR 0, it depends on the differential entropy, h of x, and on signal variance. But more, to be simple, in a simple way, this sigma x squared would be somehow cancelled in the 2 to the power of minus h of x. And what you get at the end, it's only the type of the PDF that affects h of x. So for all processes that share the same uniform variance, you would have the measure what is the final result on the quantization quality. So if this value is the differential entropy is higher, then the offset goes down. So it is a lower quality if the process is more complex to be quantized. If the process is trivial process, like this uniform process, in that case, obviously this SQNR 0 must be 0. Okay? So what should we get? For our case, this must be cancelled because this is 1. 20 times logarithm base 10 of 1. Only then we will get the 0 dB offset. Okay, so for uniform process, this SQNR 0 is 0 decibels. So the curve goes to the origin of the distortion plane. Okay, but if this differential entropy for some other source like this one is not trivial, then you have to compute it. Okay, but obviously the type of process only affects the offset of this curve, but the slope is the same. So the slope of the curve is always 6 decibels. It doesn't matter what kind of process you quantize. Always, if you increase the same, if you add 1 additional bit to the message, you get 6 dB quality additionally. Okay, so the slope is always the same. The only thing is that the offset of the curve depends on the type of the process. And that is the basic idea behind this high rate quantization theory. So based on this simplification that we substituted the actual PDF that was a function of x with a constant in a range, in a class, we could derive this final expression that relates quality and rate. And this final expression is a trivial expression, simple linear function, as before, but now we have this offset part that depends on the type of the process. And in the next lecture, we will show for several examples how this SQNR 0 depends whether it is uniform, Gaussian, or normally distributed process, or maybe some sine signal that also has a given PDF, and so on. So with few examples, we'll show how the PDF of the process affects this offset. Okay, so it is all for today. So see you in a week time.